Okay. Uh, a flywheel is mounted on a vertical shaft as shown in figure below. Okay. The flywheel is in the middle and both the ends of the shaft are rigidly welded. It cannot move. The flywheel is in the middle. Okay. Both the ends of the shaft are fixed and its diameter is 50 millimeter. The flywheel has a mass of 500 kg. Find the natural frequency of longitudinal and transverse vibrations. Take E equal to 200 giganewton per meter square. That is your question. Okay. So you observe the figure. Total length is 1.5 meter. The distance above the flywheel is 0.9. Below the flywheel is 0.6. I have declared those distances as L1 and L2. Diameter of the shaft is 50 millimeter. Young's modulus is 200 giganewton per meter square. All the things are given. Mass of the flywheel is 500 kg. Everything is given. Now the flywheel is represented here as a dynamically equivalent system. Two masses separated by a distance. Okay, this is what you have seen in the first unit. We have not drawn a thick wheel. It is replaced by a dynamically equivalent flywheel. Okay. So these are the given data. I have written down the given data. Now I am going to start the problem. Cross section area of the shaft was find a pi by 4 d square. Pi by 4 into 0.05, 1.96 into 10 power minus 3 meter square. Moment of inertia of the shaft pi by 4 d square. Pi by 4 is 64 into d power 4. So that is same whatever you have done in the earlier problem. Same moment of inertia comes here 0.307 into 10 power minus 6 meter per 4. Natural frequency of longitudinal vibration. Both questions are there. Longitudinal as well as transverse is asked. Okay. So I'm going to look at this diagram. So for finding longitudinal case here, you have to understand I'm going to split the mass of the flywheel into two. How I am going to split? A portion of the mass of the flywheel is carried by this portion of the shaft as a tensile load. The remaining portion of the mass of the flywheel is carried as a compressive load by this portion of the shaft. Do you understand? Some portion of the mass of the flywheel is carried by this portion of the shaft as a tensile load. Okay, the remaining mass of the flywheel is carried by the lower portion of the shaft as a compressive load. Now, how much is this portion of mass and this portion of mass? I am going to find out. But I know one thing. If I add these two masses, I will get 500 kg. Okay, that is the entire mass of the flywheel. That 500 kg is getting distributed into two. Okay, that how much getting distributed, we are going to find out. So let M1 equal to mass of the flywheel carried by length L1 as a tensile load. Okay. M minus M1 equal to mass of the flywheel carried by the length L2 as a compressive load. We know that extension of the length L1 equal to W1 L1 by AE. The same formula that you have used in the longitudinal case of the earlier problem. Cantilever beam suspended from. I am imagining that the shaft is only up to this. So it will resemble the earlier problem, right? Transverse longitudinal vibration of a cantilever with a load at the end. The formula is WL by A, deflection formula. Okay. There, I am going to write as W1 instead of W because it is not 500 kg into 9.81. Some proportion of that 500 kg is actually this W1. Okay. That is unknown. So keep it as unknown. W1 L1 by AE. L1 is known. L1 is 0.9 meter, which is carrying the tensile load. Okay. A is same, E is same. Only the variation comes from the mass. For proportion of mass giving tensile load, a proportion of mass giving compressive load. Okay. So M1 G1 L1 by AE. Here similarly for compressive portion, the remaining weight, total weight is W. From that this W1, if you subtract the remaining weight that is giving the compressive load, you can get this. This is actually L2, not L1. L2 divided by AE. So M minus M1 into G. This W minus W1 is written as M minus M1 into G. These two are same. Okay, so W is M into G, right? This entire thing is written as, you take G as common outside, it becomes M minus M1 into G, L2 divided by AE. Okay, so for equilibrium, these two things must be equal to each other. Which two things? If the shaft has to stay in place, the extension should be equal to the compression. Only then the shaft can stay in equilibrium. Okay, so therefore these two are equal. I am going to compare those two things and find out the value of M1. Okay, so what I can do, strike out all the common terms on both the sides. I can strike out G, I can strike out AE altogether. Okay, so M1 L1 equal to M minus M1 into L2. That's how the equation gets simplified. Correct? M1 L1 equal to M minus M1 into L2. All the values you substitute, whatever is known, you put it here. M1 is unknown into 0.9 equal to 500 minus M1 into 0.6. From this I can find out the value of M1. Correct? So it comes around 200 kg. So remaining 300 kg is the compressive part. Clear? So remaining, right? So I have found out 200 kg is giving a tensile load to the upper portion of the shaft. Okay. Extension of the length L1. Here you can put now 200 kg in W1 place, 200 into 9.81 for W1, find out the deflection. Okay, so all the data you can list down for your clarity. So 200 kg is the tensile load portion for a 0.9 meter shaft above the flywheel. Area of cross section, Young's modulus, everything is there. So substitute WL by AE. So W is 200 into 9.81. 200 kg giving tensile load to the upper portion of shaft into gravity into length of that portion above the flywheel, the length of the shaft, AE. So you solve, you will get 4.5 into 10 power minus 6 is the longitudinal extension of the shaft. Okay, so with this you can find out the longitudinal frequency. Again, you don't have to solve for the compression portion of the lower because we have already declared they are equal. If this much of extension takes place above the flywheel, that much of compression will take place below the flywheel. Only then the shaft can remain fixed in a single place, otherwise it will fail. So you don't have to again separately calculate that. You can straight away with this deflection you can go for calculating the frequency. Okay, 0.4985 by this del value for 4.5 into 10 power minus 6, it comes around 235 hertz. That completes the longitudinal portion of the problem. Okay, so now I am going to solve for the transverse portion of the problem. Could be considered to be equivalent to this, could be considered equivalent to this. If you can rotate it on the left of 90-degree left anti-clockwise, these two figures will resemble the same. So this deflection formula I can straight away take. Static deflection for a shaft fixed at both the ends carrying a point load, eccentric point load, which is not at the center. The formula is W A cube B cube divided by 3EI L cube. Okay, here I want to tell you one thing. Your Kurmi textbook has this formula wrong. Okay, in the tabulation, but in the problem they are using this L cube. So when I went through this, I got a confusion whether this is in the problem they have in the tabulation of formula they have given this as L, but in the problem they have used as L cube. This is the right formula. L cube is the right formula. In the tabulation of the formula in the before the problems, it is given wrongly. So this is the right formula. Okay. So W A cube B cube by 3EI L cube. So all these things by now you are familiar. This is A. From left to point load is A. Point load to right is B. Total length is L. E is Young's modulus. E is moment of inertia. L is total length. Okay. Substitute all the values. So that is the formula. So mass is 500 kg. For this I am not splitting the mass. I am taking the entire mass. Okay. Only for longitudinal vibration I have split the mass. So length is 1.5 meter. A is 0.9. B is 0.6. Young's modulus. Moment of inertia. Put all the values into this. So W is 500 into 9.81. Just 2 more minutes I will complete. Okay. So 509 W A cube V cube divided by 3 E is Young's modulus 200 into 10 power 9 E I L. Okay. So solve it, you will get the deflection 1.24 into 10 power minus 3 meter. So put it into the, so static transverse deflection is 1.24 into 10 power minus 3. Natural frequency of transverse vibration, put the deflection 0.4985 divided by root of deflection. Substitute that number below in the square root, we'll get the answer to be 14.24 hertz. So that completes the problem. So when I summarize the, so hence natural frequency of transverse vibration is 14.24. Summarize the results. Natural frequency of longitudinal vibration is 235 hertz, transverse vibration is 14.24 hertz. Okay, so it is taken from your 23.3 Kurmi text.